Look closely. This walkway never quite touches the ground. Wherever the earth curves, a sliver of light opens beneath it, and where the ground runs straight, the light closes to nothing. No one planned that pattern. And by the end, you'll know exactly what it measures. Here's the puzzle. We want the exact area under a curving piece of ground, the integral. Just the area under the curve. But we're not allowed to trace the curve. All we can do is drive a few posts, evenly spaced, and lay straight planks between them. Straight lumber, to measure a world that bends. Start with a single span. 2 posts, 1 plank. The shape it walls off has 2 upright sides the ground's height at the left post, and at the right, joined by a straight top. That's a trapezoid. And its area is just the average of the 2 heights, times the width between them. Half the step width times the near height plus the far height. Now lay them end to end, all the way across. Notice the posts in the middle. Each one holds up 2 planks at once, the end of one span and the start of the next. Only the very first post and the very last stand alone. Add every span together, and those shared posts earn their keep. Each interior height gets counted twice, once for the plank on its left, once for the plank on its right, while the 2 endpoints are counted just once. So the whole area is half the step width times the first height plus twice every interior height plus the last. That's the composite trapezoidal rule, the numerical integration workhorse. Degree 1 Newton-cotes. Step back and look at the finished walk. From here, it looks like it hugs the land perfectly. But watch the low places and the crests, right where the ground curves hardest. The plank and the earth pull apart. Here is where the boardwalk lies to us. And it only ever lies where the ground bends. Over a dip where the ground cups upward, what we call convex, the straight plank floats above the earth, so the estimate comes out too high. Over a crest, it cuts the corner and comes out too low. And the size of that gap is set by the curvature, the second derivative, times the step width squared. The harder the bend, and the wider the posts, the more it lies, so drive more posts. Here's the payoff. Have the spacing between them. And the error doesn't just halve, it drops to a quarter. Have it again. A 16th. That's second-order accuracy. The error shrinks with the step width squared. And on any stretch that's already straight, the plank lies flush. 0 gap, exactly right. A straight line is the one shape the trapezoid rule gets perfect, but there's a clever move than just adding posts. Ask where the plank should rest. Rest it on the post tops, the 2 endpoints, and you get the trapezoid, which leans one way. Rest it instead on a single post in the middle of the span, the midpoint rule, and it leans the other way. So blend them. 1 part endpoints, 4 parts middle, 1 part endpoints again. The 2 errors cancel. That blend is Simpson's rule, and it's 4th order, accurate enough to integrate any cubic exactly. Now change what the ground means. Let the height be the concentration of a drug in the blood, and the distance across be time. The area under that curve has a name every pharmacologist knows. The area under the concentration time curve, the body's total exposure to the drug. And how is it computed? From a handful of blood samples. Exactly this, planks laid between the measurements. The linear trapezoidal method. On the falling tail, where the curve decays, the planks are laid on a log scale instead. Linear up, log down. And the boardwalk doesn't stop at a line. Let the ground roll in 2 directions, at once a whole landscape. Now the planks become flat panels, resting on a grid of posts, a deck over the rolling land. The volume trapped under the deck approximates the volume under the terrain. 1 cell at a time. Average the 4 corner heights, times the little patch of area. Sum them all, and you have the 2-dimensional trapezoidal rule. The very same idea, one dimension higher. So why not always reach for Simpson? Or something fancier still? Because simple has its own virtues. The trapezoid needs nothing but the samples you already have. It never overshoots into wild swings. And on noisy, real-world data, that restraint can be safer than a higher-order rule chasing every wiggle. Simpson wins on smooth curves. 2 extra orders of accuracy, for free. The trapezoid wins on honesty. Neither is simply better. It depends on the ground you're crossing. So here is the whole idea, in one picture. A curve we can't trace. Straight planks between evenly spaced posts. Each span, a trapezoid half the width, times 2 heights. Shared posts, counted twice. A gap that opens only where the ground bends and shrinks with the square of the spacing. Flush and exact on a straight line. And underneath, 100 everyday measurements. A drug's exposure among them. Look again at that hovering walkway. Every sliver of light was the gap between straight and curved. The era, glowing brightest exactly where the earth bent hardest. It was never a flaw to hide. It was the one thing the method could always tell you. A straight plank lies only where the ground bends, and it tells you exactly how much.